Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 29, 2026, about 5 days ago. It introduces a streamlined framework called Manifold Constrained Steepest Descent that allows optimization on curved geometric surfaces to be just as efficient as standard methods, effectively bypassing the costly nested loops that usually slow down training in these settings. The paper is titled Manifold Constrained Steepest Descent, and as we'll see later, the improvements in stability and speed are quite remarkable across tasks ranging from simple component analysis to fine-tuning large language models. To visualize the geometric difference, Figure 1 compares a single update step on a simple spherical manifold. At the current point xt, the flat grid represents the tangent plane where standard methods usually operate. For instance, the red arrow shows Riemannian gradient descent moving strictly along this surface. In contrast, the blue arrow represents the new SPEL method. Notice how it isn't confined to that tangent plane. Instead, it cuts directly through the ambient space to find a steeper descent path, which is then projected back onto the sphere. Table 1 formalizes these update rules by contrasting unconstrained Euclidean methods in the top row with the manifold-constrained versions below. The left column covers standard Euclidean norm updates, while the right column focuses on the spectral norm. The key innovation appears in the bottom right cell, which defines the SPEL algorithm. Here, the update direction is determined by the matrix sign of the Riemannian gradient, and the result is projected back onto the manifold using the matrix sign again, ensuring efficiency without nested loops. So Table 2 translates these theoretical efficiencies into real-world speed gains for the PCA task. It compares wall clock times for standard Riemannian gradient descent and 3 manifold muon variants against the new SPEL method on the far right. The results for n equals 300 are particularly striking. While the nested loop muon variants take between 30 and 42 seconds, SPEL finishes in just over 6 seconds, which confirms that eliminating inner solvers drastically reduces computational overhead. While the previous table highlighted raw speed, Figure 2 confirms that this efficiency doesn't come at the cost of convergence quality. These charts track the distance to the optimal subspace over 300 iterations for 2 problem sizes, n equals 200 and n equals 300. In both cases, the solid blue line for Riemannian gradient descent improves relatively slowly. By contrast, the purple SPEL curve tracks tightly with the dashed manifold muon baselines, dropping rapidly toward the solution. This demonstrates that SPEL achieves the same aggressive per-iteration progress as the complex nested loop methods. Alright, Figure 3 extends the analysis to a more complex deep learning task, training a wide ResNet 28 on SciFar 100. The left panel tracks test accuracy, where the solid blue line for SPEL eventually surpasses the dashed orange line for muon, reaching a final accuracy of nearly 80%. In the middle panel, we see that while muon minimizes training loss much faster initially, this aggressive fitting doesn't translate to better generalization. Finally, the right panel confirms that SPEL achieves a significantly higher peak accuracy across valid learning rates. Table 3 details the numerical results for that wide ResNet 28 experiment. In the first data column, SPEL achieves the highest test accuracy at nearly 80%, clearly outperforming both the standard Euclidean optimizers and Riemannian stochastic gradient descent. In contrast, although muon achieves a tiny training loss, its test accuracy lags behind at roughly 77%, confirming the overfitting issue. The final column shows that while SPEL's per epoch time is slightly higher at 40 seconds, it stays within a competitive range compared to the 34 seconds for muon. Moving from computer vision to language tasks, Table 4 evaluates the method on large-scale adapter tuning using llama models. Here, the authors compare SPEL against Stella, a state-of-the-art optimizer that specifically handles Stiefel constraints. The table breaks down performance across 8 common-sense reasoning tasks. Crucially, looking at the average column on the far right, we see that SPEL matches the baseline almost exactly, with both methods scoring around 86.5%. This demonstrates that SPEL can replace complex, memory-heavy optimizers in large-scale settings without sacrificing downstream accuracy. Wrapping up, the big takeaway is that manifold-constrained steepest descent successfully brings the speed of standard optimizers to complex geometric spaces. By replacing costly inner loops with a direct projection step, specifically in the SPEL algorithm, it offers a scalable path for training stable, high-performance models on manifolds. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.